Bonjour à tous. Hello everyone. So I'm gonna talk a bit about the work I did for implementing elliptic curve pairings in Cairo. And my talk is about verifying snarks. So first, a little bit about me. I'm a Cairo developer at OnlyDust. I have a background in cryptography, and I was previously in academia where I studied theoretical computer science, and I also worked on end routing, which is a routing method for the Bitcoin Lightning Network. So first, a little bit of background. So what are snarks and starks? So maybe you've heard about them. It's two families of protocols for proving instances of a computational problem. So, and the main difference between them is that snarks are succinct and non-interactive. Succinct means that the proof is rather short, and non-interactive just means that you don't have to go back and forth. You just generate a proof and the verifier can verify it right away. And they are both argument of knowledge, meaning that you have a computation and you can prove that the computation actually operated. While starks are scalable and transparent. Transparent means that there's nothing hidden, nothing up my sleeve, meaning we are not relying on some trusted setup or random thing that needs to be hidden. And they are scalable, meaning that the verification in itself is quite efficient. So why not have both? Why can we have both of the best of both worlds? So first, why do we want to implement snarks in Cairo? So first, I need to remind that StarkNet is not a ZK rollup, it's a validity rollup, meaning that right now there is no way to do zero knowledge proofs in StarkNet. But StarkNet is actually general purpose, meaning that you can have any computation you want. So since this kind of, since snarks and starks were invented before blockchain, kind of, then it means that why not implement snarks in Cairo? It should be possible. And why is it useful? Well, because right away, if you can implement them, then of course, since snarks can be ZK snarks, you can have zero knowledge proof inside Cairo for free, right? And also, as a byproduct, you get compatibility with existing dApps, such as Tornado Cash or any private game or private application that already exists. And also much more advanced topic that I might talk about at the end of the talk. So snarks, how do they work? Basically, you are given computation, which is represented with a program that takes a public input and a secret input. And when you execute the program, you get some output. And generally, you have a prover that wants to prove he knows some secret inputs, such that it gives this output. And he wants to convince a verifier that the program ran correctly. And the big part of zero knowledge proof is that he must do that. He must convince a verifier, and the verifier should not learn about the secret input. For ZK snark protocols, the way they work is that we have a trusted setup that takes as input the computation represented as a circuit and spit out some keys. And you have two functions. You have the function that is executed by the prover who needs to generate a proof given the inputs and the secret, the public input and the secret input. And the verifier takes as input the proof and the input and the output of the program, but does not take, of course, the secret input. So it means that the verifier should be able to verify the computation without knowing the secret input. That's what gives the zero knowledge property in some sense. And the main idea of ZK snark protocol is to represent a computation, so a program, as a polynomial. how do we do that? Say polynomial is a bad word. So this is, I want to convince you that you already know how to do this because probably you've already done this in Cairo. And this is a toy version. This is not exactly how you do it, but this is a way to make sure to understand that it is possible. So for instance, you can define a secret function that takes as inputs A and B, which are, let's say, the public parameters, and W is a secret input. And you will do something based on the value of W. If W is 1, you will return A plus B. If W is 0, you will return something else. And this encodes some conditional thing with ifs, but actually you can rewrite this function just as in one line as a polynomial in W. So just you can convince yourself in this return that when W is 1, then this is 1 and this is 0, so you get A plus B. And when W is 0, you get exactly the second return. So this is a way to encode a computation into a polynomial, and probably you've already done it to avoid revoked reference or something like this. So how do we generate a ZK proof? The main idea of what a proof does is you check the program, you construct a big polynomial that will encode the computation in some way, and you make sure that it satisfies the original constraints, meaning that it matches a program that will, for instance, just take the input and the secret, that we just take the input and spit out the output. So this is the most simple program that is a proof, but it doesn't encode the computation. So what I mean is that when you construct this big polynomial, you want to make sure that it is a multiple of another polynomial, which is a simpler program, which represents the constraint. And of course, you don't just want to send this polynomial as a proof because it encodes all of the computations. So it means that the coefficient actually encodes the secret input in some way. So you want to encrypt this polynomial so as to not leak the secret input. Enters elliptic curve cryptography to do that. So I didn't want to show you the usual elliptic curve thing, but I want just to give you an idea of how it works. So generally, an elliptic curve is a mathematical object where you have a generator point, and you can, so in this example, we can create a public key and private key pair, just using the properties of an elliptic curve. So how does it work in here? Just say that the generator point is the original, the initial position of the ball, and the private key encodes the angle and the force that you put on the ball. So when you actually launch the ball, then it will appear, it will go at some place, but and the final place will be the public key, let's say. It's something public. When you publish this, then you have no way to go back to the original private key, because whenever, if you take a random position on the billiard, then you have no way to know, even if you know the original point, you have no way to know which is the force you actually applied first and which is the angle. And so this is a basic way to understand how to compute a public and private key pair, but actually what we get from elliptic curve cryptography is much more than that. We get something that's called homomorphic encryption. What homomorphic encryption is, actually we want two properties. We want property, an additive property, and we would like to have a multiplicative property. The additive property should be clear. It means that when you have, let's say, two private keys, then you can actually compute the public key of the sum of the two private keys just by adding the two public keys. So it means that when you encrypt together, when you encrypt two values separately, it's actually the encryption of the sum. And you will also think that you can have multiplication, that imagine you have two private key, you multiply them, and maybe it's just the multiplication of the encryption of those keys in isolation, but actually it's not, because it's not well defined. But you can get this with a pairing. And a pairing, in really a short way to explain what a pairing is, it's something that you can construct on supercharged elliptic curve that will have this multiplicative property, and I will explain why we need it. Okay, back to snark. How do you verify a snark? The verify recipe is actually, it's not simple, but okay, bear with me. Remember that you have encoded your computation as a polynomial that must have a certain form. So the polynomial is p of x, which must be a multiple of the constraints, c of x. And actually what you have is you want to encrypt that so that we don't know what the polynomial is. So we use homomorphic encryption to encode the values of this polynomial. And what you want to do is that you want to check that when you send that to the prover, you want that the polynomial, you want to check the multiplication, actually, that the polynomial is actually a multiple of the constraints. But you don't want to just check it like that. You want to check it hidden in the exponent. And to do that, you need that multiplicative property, because here you are just saying, okay, my polynomial is actually a multiple of something. So this is the property that is critical for some kind of snarks, and that's why we need the pairing operation. Okay, how do we do pairings in Cairo, and why do we want to do them? So it's actually something I implemented in Cairo, but I can show you the architecture model. So usually you want to, so on top you have application, let's say Tornado Cache. They will use a zk-snark protocol, so you have a protocol just below, and the protocol we call a pairing. So you need to implement, now we know that we need to implement a pairing. How do we implement a pairing when the low-level backend is Cairo? So you have to work from Cairo. Okay, we have felts. Now from felts, felts are finite field elements, but for this particular elliptic curve, they are not the same size. So you need somehow to construct new types to encode new finite fields operations. From these finite field operations, you need to now encode, construct all the elliptic curve operations, and somehow supercharge them, and then you get a pairing. So implementation details are quite boring, but just to show you why this is quite intensive, I did a benchmark, and one pairing just takes 1.5 million steps and took about 90 seconds on my computer. And usually for a snark proof, I think you need to run like at least 3 of them. To implement this, actually you can use hints to accelerate some things. Like you can offload all of the algebraic operations and just check them, which is really helpful in this case because they're really intensive. And I think if you recode the whole thing just in pure Cairo, it's probably a large factor and is probably a few billion steps. And so still, 1 million steps is a lot, but maybe you can have a built-in. You can, okay. The thing is, you might want to have this as a built-in so that you don't need to spend 1.5 million steps. And in order to do that, you need to make sure all the hints don't do anything crazy. So you need to whitelist the hint with Starkware. Okay, can you use this? And actually, yes, because so first, if you can already do this on Ethereum, and it's actually a precompile that has been added, and that costs at least 45,000 gas, which is the most expensive operation opcode in Ethereum, and actually it was more than that, but they reduced it, and it's still the most expensive one. So it's possible in Ethereum, but it's insanely costly. And Lambda class, shout out to them, they did a circum export to Cairo, so now you can have your own circuits, create them, and instead of verifying them on Ethereum, you can compile them and have them verified on Cairo. For the endgame application, well, the first one is that since it's an Ethereum precompile, it means that it's one of the steps to be able to do anything that Ethereum does. So we want to have Ethereum parity. Once you have that, then you can say that StarkNet can do anything that at least anything that what Ethereum does. And then, for instance, if you couple that with Fossil, then you get even some more mind-blowing stuff, like you can even understand what Ethereum does because you have access to the storage. And you can do some operations on it. I implemented this so for the pairing curve in Ethereum, but using this work, you can kind of modify it to implement any kind of other pairings because it's not the only pairing. And with that, you can magically get other kinds of cross-chain compatibility with so with ETH 2.0 and with Zcash. So magically, if you just do the same math, then you understand what Zcash does inside StarkNet. And as I said, since now with snarks you can get zero knowledge, then you can think to have privacy as a service. So you can imagine building a layer 3 where you use this opcode, this pairing to create an actual ZK rollup over StarkNet. It's probably not the best way to do it because it relies on a trusted setup, but it's still a way. It still shows that it's possible. And yeah, and then sky is the limit because you can. It's just up to your imagination what you can do. If you want to do dark DeFi pools, anything, games, ZK games, mental poker, etc., etc. Okay, so if you want to look at the code, it's here. You can follow me on Twitter if you want to learn more about my work. And this has been Verifying Snark on Starks. Thank you.